I'm your host, Sean Kelly. I am the Director of Sales Operations. I oversee our sales operations team, inside sales team, and customer service team. I've been with Onset for about 13 years, almost 14 now. And one of my roles, I have various roles, but one of my roles was an account development manager specializing in our indoor environmental market. Some details about our webinar today. It will run for approximately 30 to 40 minutes. We'll save about 15 minutes at the end for some questions. Reminder to type your questions in on the right-hand side there. You'll see a little questions box in the control pane. And then the webinar will be recorded. So when you receive an email after the webinar, it will have a link to view it again if you'd like to. A little bit about HOBO Data Loggers. We make HOBO Data Loggers. We're located on Cape Cod in Massachusetts. Our sole focus is data logging. It's reliable, accurate data logging. We're a world leader in loggers, and we have a global network of distributors. We are ISO certified, and we've been around for a good 43 years now. And today's guest speaker is Steve Di Giacomo. Steve is a mechanical and HVAC engineer. He's the principal commissioning and energy engineer at EMA Boston. Welcome, Steve. Thank you for doing this for us, and I'll hand it off to you now.
Thank you, Sean, and good afternoon or good morning to each and every one of you. Glad you could join us. I've been practicing engineering now for about 40 years, and the agenda today, we're going to talk a little about the value of data. We're going to go back in the Wayback Machine to 2022 and talk about some school openings. I should say that we some town buildings that were reopened due to COVID, and how ASHRAE 62.1 factored in. I assisted in the reopening of many New England town buildings, libraries, schools, offices, police stations, Department of Public Works, senior centers, etc., using a combination of dilution ventilation and fibrous air filtration for classrooms, and ultraviolet lamp system designs for rooftop unit air handlers, and also upper room UV wall units for cafeterias and gymnasiums. Sometimes we did a combination of both. Also nursing offices have sick bay areas for children, students that are unwell. And we did some UV, upper room UV, where we can get upwards of 10 effective air changes per hour, which will help reduce the risk of transmitting infectious diseases, which is the primary focus of today's topic. To this day, the Healthy Buildings Program at the Harvard's T.H. Chan School of Public Health recommends a minimum of 5 effective air changes of either filtered air or ventilation, dilution air, or a combination of the two for all space types. Sort of a one size fits all. And all of my designs have always strived for about 6 effective air changes per hour, simply because we don't have, or we did not have, a testing method or validation. So we would aim high and hopefully hit the target of 5. And, you know, we'll see in a moment that ASHRAE 241 introduces methods and testing for validation. And we'll get there, and we'll talk about that a little bit more later. As you may or may not know, ASHRAE 62.1 is a ANSI standard written for primarily odor control caused by contaminants in a building, for example, mold, furnishings, carpeting, adhesives, occupants. Yes, we are a source of contamination in a building. And it offers a differential CO2 technique for determining and controlling ventilation dilution error vis-a-vis demand-controlled ventilation, you're more commonly referred to. In our previous Lunch and Learn we did a couple years ago, we combined the ASHRAE 62 in conjunction with the Harvard T.H. Chan School of Public Health Healthy Building Program. I think we have a link for that a little bit later on if you want to download that. And we will review that method today. That method is still being used today. ASHRAE 241, 2003 is now completely through public review. We're going to focus on that as well today. It's a brand new standard. It's currently not accepted by any states. And it essentially abandons the Harvard SPH minimum of 5 equivalent air changes an hour in deference to an equivalent clean air flow CFM per person based on space type. This is not the same CFM per person in ASHRAE 62.1. That CFM per person is based solely on dilution air. This is a combination of dilution air, fibrous air filtration, filters in other words, and ultraviolet irradiation. That can take place either in the air handler or the return duct of an air handler, or actually upper room in the actual zone. So in my estimation, regarding challenges, ASHRAE 241 is off to a good start. We can expect many addendum for clarification. This standard will continue to evolve. It's not going away. Probably you'll see some early acceptance in a year or 2 or 3. What I think we need are more companies that can perform the in situ validation via aerosolized release of tagged DNA. They're using a challenge organism. They specify MS2, which is a macrophage organism. It's a challenge organism is non-pathogenic to humans, and it has a known K factor. UV K factor. So they can set up and release and make determinations in terms of equivalent air changes per hour, much as we did with tracer gas studies. Same math. We should also keep an eye on any new modalities that are being developed. For example, I talked about UV. All of the UV that I've designed systems for was a mercury lamp 253.7 nanometer wavelength. We should keep an eye on the far UV at 222 nanometer. And I do believe that we'll need additional research on ultraviolet K factors in air at various relative humidities for not just the challenge organisms, but some of the things we're trying to combat: SARS, avian flu, maybe TB, so on and so forth. I'll tell you, based on my review of the research, K factors for SARS have a plus or minus 25%. So we really could use better research, more research to tighten up on these numbers. And as far as strategies, I don't know why it's there twice. We have some strategies today that we can offer to help with, eating your cake and having it too. The first thing you should do is, before you put pencil to paper or compute a design, you should determine what the design occupancy is, because remember, the ASHRAE 241 is a per person standard. So knowing what the design occupancy is and what might be the, we'll call it pandemic occupancy is really important, because that'll obviously be a reduced occupancy. For example, I think we're all familiar with the notion of having half the students show up for class on alternating days. That would be a really sensible way to keep costs down and maintain the standard without having to build in too much filtration or UV. You can only do so much with dilution ventilation before conditioning the air becomes a real cost problem. You should consider choosing retrofit designs with UVC lamps at the air handler rather than MERV 13 or MERV 11. Has been our experience. It makes less sense to invest in UV lamp designs after you've upgraded your air filter system. And the converse is also true. So in other words, one system will affect the other in terms of performance and return on investment. Always err on the side of healthy building because, for example, for office buildings, a building-wide drop in human productivity of just 1% or an increase in absenteeism of 1%, oftentimes we find is equivalent to 100% of the building's energy usage. So this could be very important. Building health. Value of data. Data is important, and thanks to HOBO products, instead of drowning in data, we are able to make sense of it and interpret it and use it in a myriad of ways, turning unknowns into actionable opportunities. Data logging can provide you better inputs for, say, a energy 3D simulation model, or back of the envelope calcs. You can verify chilled water reset schedules and things of this nature. You can evaluate new technology that's just recently come on the market. Does it really save what the manufacturer says it saves? So we are involved heavily in that type of use of loggers as well. So this is a typical chart that I often put together for clients. It's a Friday to a Friday, full week of data pulled together by HOBO software from 3 different HOBO devices. And it's as simple as copying and pasting. And one device may have a 10-minute interval. The other device may have a 5-minute interval. The other one could have just a change of state interval, but it seamlessly integrates everything together. The scaling, we just see here we have, an X and a Y, 2X, an X, a Y, a second Y, a third Y. You can keep going, and it keeps changing colors. You can choose line thickness. You could choose colors. These are all default values, so I'm quite happy with this. You can also export to Excel and run your own chart if you wish. This chart, as you can see, we have temperature, relative humidity, light intensity, CO2, outdoor air temperature, and the supply fan motor for the fan system. And we arrive on a Friday afternoon. You can see the lights are off all weekend. They come back on Monday, Tuesday, Wednesday, Thursday, and Friday afternoon we came and picked up the loggers. You can see we caught the tail end of Friday. Here's your CO2 peaking. Here's your baseline CO2. You can see it's running about 480 on the baseline. It's probably gets down a little bit lower. The sensor could be out of calibration a little bit, but we're interested in the differential. And this shows that, we're probably running about 60 CFM per person based on the differential CO2, which probably suggests either we have very low occupancy, or we have a VAV box possibly that's stuck a little bit or open than it should, or the min on the box is set at 50% where it could be set down at 20%. Under ASHRAE 90.1, you would definitely want to do something like a 5-to-1 turn down. So You can check economizer free cooling opportunities, whether you missed an opportunity or you're in economizer when maybe you shouldn't be, so on and so forth. All right, so let's continue. Using the differential CO2, this is an equation right out of ASHRAE 62.1, ventilation for acceptable indoor air quality. We can quickly determine, based on the differential CO2, which is here in the denominator, CFM per person for steady state conditions. And for classrooms where the kids are in the classroom for 40 minutes and attendance rolls are pretty accurate in the municipal level, actually they're very accurate, we can quickly surmise the amount of fresh air coming in by multiplying the CFM per person by the number of students on the roll that day. That in turn can be brought into this third equation, which is CFM of OA times 60 minutes per hour divided by the geometry of the room, the length, the width, the ceiling height, and we can quickly determine ventilation in air changes per hour. Here's the link to the Harvard Buildings program. This will be available later as well, as Sean indicated, from the Harvard T.H. Chan School of Public Health, page 5, third bullet. It's still there today. This is still in vogue. Again, the goal, 5 air changes per hour. So before ASHRAE 241 came out and got published, I would look at these differential CO2 in these classrooms and determine how much portable HEPA filters we needed to bring in and evenly disperse around the room. Always try and oversize. If you can afford to, oversize your HEPA so you can run them at 50% speed and keep the white noise to a minimum, because the #1 problem in teaching is noise, distraction. Just a quick mention, Dr. Joseph Allen, associate professor at Harvard, put this together. So this standard refers to engineering controls, and by that they're talking about modalities: dilution ventilation, air filtration, fibrous air filtration using filters, and air disinfection. Disinfection, in my world, that would be ultraviolet mercury lamps. You could do ozone generation. However, you would have to do that when the building is unoccupied, and that could be dicey because you never know when people pop in. So the goal of this standard is, again, to reduce acquired infection rates. Maybe you're all familiar with the term hospital-acquired infections. Well, we want to deal with that with this standard. We also want to extend that to other space types, such as school-acquired infection rates and office-acquired infection rates. We want to instill trust in the safety of indoor air quality vis-a-vis performance-based testing certification in situ. Yeah, you can test out the air handler, but also you can certify zones in a building, floors within a building, so that when a cognizant authority basically says we're in pandemic mode, you can operate your building in pandemic mode. One of the strategies, I'm not sure if I mentioned it earlier on in the agenda slide, would be installing technologies or modalities that you can switch off. Otherwise, you have to live with it even after the pandemic or the bioaerosol alert is over. So again, the standard introduces equivalent clean airflow as defined as the minimum equivalent clean air breathed required in a breathing zone to mitigate long-term transmission. So that's the airflow, and the ECA is the per person airflow. The IRMM is the infection risk management mode. Prior to this standard coming out, I just referred it as pandemic mode. So we could also take the airflows and calculate dynamic equivalent air changes per hour and compare it to the standard. The standard, this is actually table 5.1 from the standard. These are the equivalent clean airflows and expressed as CFM per person. And again, this is total air that's been cleaned. It's not necessarily all ventilation air. And we can see for offices, it's 30 CFM per person. Classrooms, it's 40. Waiting areas, more like 70 to 90 here for healthcare. I think a normal waiting area is more or less 70. This can be challenging under the standard to be certified at these levels. And I'm going to show you, this standard comes with a downloadable spreadsheet calculator. We're going to run through that really quickly. But before doing that, I took the CFM per persons for a classroom, call this K through 3 or K through 2, and then K2 through K12, office, food, beverage. Going with standard ASHRAE 62 densities for design purposes of spec space. It's 25 per 1,000, 35 per 1,000, 5 for office per 1,000 square feet. Typical classroom sizes are 900. So basically, if we calculate using the volume of the room and using the airflow per person times the number of people for density, this is going to normalize out to 6.7, 9.3, 1, and 36. Compared it to the Harvard Healthy Building Equivalent Air Change Standard of 5, 34% increase, 86% increase, 80% decrease, 620% increase. So overall, except for offices, this standard is raising the bar, if you will. The reason offices is low is, again, it's per person. So to meet the standard, reduce your population. That's the takeaway from this message. And following simply ASHRAE 62.1 will get you 37% of the way towards meeting the ASHRAE 241. Remember, you always have to maintain ASHRAE 62.1. It's still a prerequisite. This is equation 6.1. It basically is written for a per zone. So this would be your zone fraction. If you have 100 rooms, say this is 0.01. This would be your total outdoor air at your air handler's filtration. You get no credits for it whatsoever, and you'll see this when we run the calculator. For anything that's MERV 10 and below, you get 0 credit. You have to be a MERV 11 to begin getting clean air credits, okay? And And now you're in the room, you're in the zone. So Z goes away and we have clean air delivery rate. We have natural ventilation. And of course you have to meet this number on a per person basis. So here is the calculator that you can download. And I think it's a little busy. There are a lot of rows. It's gonna be a little confusing. I added some pictures basically, or and I broke it into two pieces. This is all your input, and this is your results page. And what I'm going to do now is I'm going to toggle over to an Excel spreadsheet. I had chosen one of the tougher rooms to meet because office is almost trivial. I mean, honestly, I'm not even going to go through an office exercise. I mean, it's so easy to meet the office with basically almost just reducing population a little bit. You could roll in some portable HEPAs, but let's take something that's really hard to do. This is a waiting room. There's a drop-down menu. And when you select here, it should choose the corresponding clean airflow rate per person. For a waiting room, patient waiting room, it's 70. I'm doing everything as though it's a zone, but so the zone area, I'm going to go with 1,000, 9-foot ceiling. It calculates the volume. Using ASHRAE 62.1, we're going to use the 0.06 CFM per square foot times your area, plus an additional 7.5 CFM of fresh air per person. So that's our outdoor air into the space. Design occupancy, 50 per ASHRAE 62, if, you know, for spec office or spec space. We're going to look at it at 10 as well. We can look at it both ways. At the very bottom of the calculator, you get to re-choose whether you want to see if you pass or fail based on design people or reduce design based on the fact that you're having, you're operating your building in pandemic mode. And this will simply calculate based on the target flow per person times the number of people. It'll calculate the design clean air flow for the zone. So if we have a MERV 10, we're not going to get any credit. If we were to make this a MERV 11, it would filter out 60% of the challenge organism, which is a macrophage MS2 challenge virus. So selecting absolutely nothing at face value other than your ventilation air coming in for design, we're about 12% of the standard. If you operate with reduced people, you get to about 62% of the standard. Go back up, we try option 2. Option 2, everything's the same. We're going to introduce, this is, this version of the spreadsheet's color-coded, and on the left column, you know, basically to remind us we want some building data here. So we're working with a patient waiting room. It's probably one of the more challenging zones because they're pretty high density area with a high requirement of 70 clean air CFMs per person. Standard area, 1,000, just per, you know, this is our standard zone. 9-foot ceiling. Volume of the room, this is all calculated for you. Total airflow, we're basically going up design airflow of 1.2 CFM per square foot of total air. We're using the ASHRAE 62.1 ventilation determination at 0.06 CFM per square foot, plus an additional 7.5 CFM of ventilation dilution air per person. Here's the design occupancy density per ASHRAE 62. This is a number that you would work with your owner to determine what the reduced occupancy could be during a pandemic mode where you're operating in risk management mode. This spreadsheet automatically will calculate your equivalent airflow requirement based on the 70 CFM, but you can base the number on either the 50 or the 10, and that is, so you can go back to the bottom of the spreadsheet when you're done and see if you would pass under pandemic mode versus design mode. You can see under reduced occupancy, you're at 62%, you still do not pass. At design, it's 12%, you definitely do not pass. When we introduce a MERV 11, we begin to get credits. 60% of the airflow will now be credited. Of the remaining airflow that needs to be cleaned up, you can apply UV. It's probably not worth it to do both. You'll get very little additional benefit. Just to show you, we're at 17, call it 18 CFM equivalent clean air per person. My apologies. And then if we simply add to the MERV a 1 log UV inactivation with ultraviolet lamps, really things don't improve a whole lot, right? So we should do one or the other. And remember what we said, when I have a cake and eat it too. So don't put in something that's a permanent pressure drop. Go with 90%. It's a permanent pressure drop, but it's tiny. And the lights can be switched on or off depending on whether or not you're in risk management mode. We're still not passing. In order to pass, we're going to need to introduce either upper room UV. We can choose 10 air changes per hour, multiplied by the volume of the room, divided by 60 minutes per hour. So you would design a system for 10 air changes per hour. One system, 10 air changes per hour of the upper room. Let's put a 0 here for quantity. Let's see if that will do it for you. Still doesn't do it for design occupancy. So let's add 4 250 CFM HEPAs in the room, in the waiting area, and disperse them. We're almost there. We're at 84%. We have 1,000 square foot room, easily fit in 2 more. Remember, even if each of these are giving you 250, size them for 500, run them at half speed. It'll reduce the white noise considerably. And you have some extra oomph if you need it. Now we're at 98% of the standard for a full complement. It wasn't all that much of an effort. We have the MERV 10s taking 0 credit for filtration. We have some UV in the unit. You put it in the return of the unit where the air is warmer, you'll double the output of the UV. This is where the dosage engineering come in. So you can save a lot of money with the installation if you can find access to your return on your unit. There are a lot of tricks when it comes to dosing engineers, including the reflectivity of the ductwork. That's a huge factor in designing the proper dosing. So you deliver the kill dose. We can do a future seminar on how to do UV dosing. But remember, I said earlier in the agenda slide, we really need to know more about the K factors for these microorganisms. We need to know more about lamp design. We can do up to 500, 500 feet per minute. We can do a 2-log inactivation in 0.1 seconds. You're probably at 60 watts per square foot of plenum, but it's doable. All right, so I think you're getting a feel for this, and I think now we should probably open it up for questions.
Have you evaluated far UV technologies?
Yes, you cannot get the power density or the intensity to eliminate. You can't deliver the dose in the time allotted. Oftentimes, you only have 2 feet, maybe less than a meter of air traveling at 500 feet per minute. You don't have the time. It doesn't have the horsepower. It's LED, and it's a diode, and it's going to overheat, and they have some real serious heat dissipation issues. Of course, in an airstream, you should be able to overcome them. But right now, there's a cost factor. But we'll get economies of scales working on our side in the future. It's definitely something you want to look at. It really, I don't know if you know about the dimerization effect of UV on single-stranded RNA, but it can really disrupt these organisms very quickly. The only problem with 222, and by the way, it's not harmful for humans. At least we don't think it is, based on a number of studies at Columbia University in New York City, or at Presbyterian Columbia Hospital. So it's promising.
Thank you to everyone for coming on here. Also, to let you know that we are on social media, so Facebook, LinkedIn, Instagram. And also, if there's anything you need, by all means, you can reach out to our sales folks at Onset. You can reach us at sales@onsetcomp.com. And we also have technical support available Monday through Friday from 8 a.m. to 6 p.m. And that's through email, chat, phone. And that's about it. Yeah, so if there's anything you need, by all means, reach out to us and we'll be happy to help you. And with that, I think we can end the webinar. So thank you very much for everyone in attending, and thank you, Steve, for presenting.